Okay, here's page 3, the alternate starting point of homology notes 1. I start here with terminology that starts with a cell complex and gives a bunch of groups, a whole sequence of groups. We'll start with a space S that is found as a cell complex, and so that means it's made out of some points, which are zero-dimensional disks, D0, line segments that are one-dimensional disks, D1, two disks, D2, etc., on up through Dn. Once they're glued into S, like when we show how to glue the the line segments into the points and the two disks onto the line segments, the N disks are called N cells of S. All right, so here's the definition. We say the N chains of S are linear combinations of the N cells. Right, so that means we're actually going to take the N cells, say for instance the 1 cells, the line segments, and the line segments are going to be the generators of a group. But it's going to be a linear group. We're going to allow addition instead of some arbitrary product. That means that it's forced to be abelian. And that means that when we add several of them together, we can say that's multiplying by 3 or by 2. Then when we multiply it by constants, it's a linear combination. We're going to use integers for the constants for now. So here's some examples so we can make this more clear. So this on the left is the familiar space real projective plane. And I've labeled all the cells. This real projective plane is constructed from a rectangular 2-cell, which has its left and right glued together with a flip, and its top to bottom glued together with a flip. That means there are 2 corners, X and Y, and there are 2 1 cells, A and B. Also, I called the 2-cell inside capital A. That little arrow inside, the orientation, that's what we're going to use to find the boundary, which is back on page 1. For now, though, here are some chains. So A minus B minus A, that's a 1 chain. It reduces to just negative B because A minus A is a commutative group. But it's a 1 chain because it's a linear combination of the 1 cells. 2A plus 3B is a 1 chain also. B by itself is a 1 chain. It just happens to have 0 A's. X minus Y is a 0 chain of P2 in this cell complex construction. X and Y are the 2 corners. 3x minus 5y is also a 0 chain. And any combination, in fact, just y by itself or just x by itself. Capital A is a 2 chain. That's the 2-cell glued in. And minus 7a is also a 2 chain. In fact, any multiple. And for now, we are using integer coefficients for the multipliers. So here's the definition of the group that we want. We'll call it C sub n of S. It will be the free abelian group of n chains. All right, that means that it's a group. It's generated by the n cells of S. So, for instance, C1 of S would be generated by A and B above. It's abelian means that it's commutative, that we're going to allow all operations to the orders to be switched. You can write A plus B or B plus A. In fact, that's why we're going to use the plus or minuses. Instead of using multiplication, we'll use addition just to show that it's commutative. The fact that it's free means that there are no relations in Cn of S. That means the only relation is that x times x inverse equals e. But we're going to write that as x minus x equals 0, since the operation is plus. We'll let the identity be 0 now. There's a note on the side, but first, another word for a free abelian group is a z-module, which I'll just mention that. We might see it again. It's over the basis of cells. In other words, you can call the generators the basis. The collection of generators is like a basis. And it's very much like a vector space, except that we're not working with a field, we're working with the integers. All right, and now if you haven't learned about the boundary operator yet, go back to page 1.